Do you ever wonder what is at the center of the universe? If so, you'll get the information you're looking for in this video, as I'll discuss whether the universe has a center or not. To know everything about it, you need to watch the complete video. Let's start the video. The universe looks the same no matter which way we turn our telescopes, or how far our detectors can detect objects. The density of ordinary matter and dark matter, the temperature of the radiation we see, the number of galaxies, the sorts of galaxies, the star populations inside them, and even the direction in which we gaze are all consistent, regardless of which way we turn. The average difference between any two areas is about 0.003%, or around 1 part in 30,000 in the biggest universe size. It's not the direction of our gaze that has the most impact, but rather the distance at which we cast our gaze. The more we gaze into the cosmos, the further back in time we perceive, and the more the light from distant objects is skewed towards longer wavelengths. When individuals hear this, a standard mental image occurs. The more the light is altered, the quicker these items move away from us. You may find the center of the universe by looking in all directions, and then asking yourself, at what point in space would we observe all directions receding equally? But there's a little problem with that. Here is the truth, as far as science is concerned, about where the universe's epicenter really lies. When an object approaches, its waves become more compact, with fewer peaks and troughs, and when waves retreat, their crests and troughs seem rarefied, not compressed. The pitch of a fire engine, police car, or ice cream cart varies as it moves. This also applies to light. The Doppler effect illustrates how motion modifies sound waves. In terms of light, a variation in wavelength doesn't affect pitch, but rather the energy to illuminate. Longer wavelengths reduce the light frequency, energy, and redness. Shorter wavelengths increase the light frequency, energy, and blueness. Due to the universal dispersion of matter, we may presume that every object's mass contains atoms and ions. Knowing which atoms are present and observing a systematic change to their spectral lines, we may calculate how much light has been redshifted or blueshifted. This reveals something remarkable. For nearby objects, red shifts and blue shifts indicate speeds of a few hundred to a few thousand kilometers per second. Galaxies at the heart of large clusters may approach 1% the speed of light, while those further out, like the Milky Way, peak at lower speeds. Everything becomes redder as we go further away from things, but the speed range stays the same, hundreds to thousands of kilometers per second. Research shows that redshift rises with distance from the sun. Is it because the object moves between emitting light and us measuring it? Because the universe is growing. Maybe the light is constantly moving as it passes between us and our research item. First, objects exist and move across space. Second, it's not so clear. According to Einstein's general theory of relativity, space is a dynamic fabric that changes through time and as a function of the matter and energy it contains. When a lot of mass is concentrated in one location, space bends to accommodate it, causing quantum particles to take a path whose geometry depends on the mass. The total solar eclipse gave the first unequivocal test of Einstein's predictions that gravity obeys special relativity, contradicting Newton's universal gravitation theory. General relativity. General relativity requires that a world with constant matter and energy can't have static spacetime. Any such approach compromises your universe's stability, causing it to expand or contract. When spacetime contracts, light's wavelength shortens. When it expands, it lengthens. The evolution of spacetime affects how light travels across the universe and reaches human eyes. Two effects might coexist. Light throughout the universe experiences regular changes due to the expansion and contraction of the universe, and the movements of galaxies and other light-emitting objects. Basic principles can't explain the condition of the universe. General relativity's equations follow the rule that the same issue may have various mathematical solutions. Observable material abundance is compatible with a growing or shrinking universe. We expect to detect strange velocities due to the gravitational attraction of other matter and energy in the universe. Every change in a single item may be due to their synergy. It's hard to distinguish cosmology from non-cosmological light shifts from a single source. We may put together the universe's expansion by seeing multiple things at varying distances. The evidence for an expanding universe is overwhelming and agrees with general relativity's predictions of an evenly filled universe with varied matter and energy. First noted in the late 1920s, Given adequate knowledge about the universe's composition and expansion pace, general relativity's equations can predict its size, separation distance, and instantaneous expansion rate at any moment in the past or future. If so, the expanding universe is nothing like an explosion, when everything goes outward from a central point at varying speeds. The expanding universe resembles raisin-studded bread. Space is the dough, and galaxies are the raisins. As the dough rises, the raisins spread outward, but don't go through it. Each raisin considers itself to remain static, yet the others it can see recede from it at various speeds. Is it possible to determine the diameter of this ball of dough, our position inside, and its exact center? If we could look beyond dough, we could answer this question. The universe is uniform within 1 part in 30,000 to the boundary of our perspective. Due to the Big Bang 13.8 billion years ago, humans can see 46 billion light years in all directions, and the universe is astonishingly uniform. There are no limits on the size of the ball of dough that represents our universe, the size of the unobservable universe beyond our visibility limit, the topology and connectedness of the unobservable universe, or the allowable shapes for the limits of our universe, including whether it has a center or not, whether it is finite or not, and where we are about any larger structure the universe may have. We can only infer that the universe seems compatible with general relativity, and that any observer may make the obvious but false conclusion: I'm at the center. This is like a raisin in the dough that can't see beyond the ball. We're in the center isn't true. The sole benefit of our location in space is that the objects nearest us are the oldest and most advanced we can observe today. Growth is slower nearby than at more enormous radii. The cosmic component of redshift affects nearer objects less than distant ones. Since nothing in the visible universe can propagate faster than light, their light must have been emitted in the past. To witness things when they were younger and closer to the Big Bang, when the universe was hotter, denser, and expanding faster, the light had to be stretched to longer wavelengths on its way to our eyes. The cosmic microwave background, or Big Bang radiation, is the only thing we can use to pinpoint our location, as all directions seem uniform from our vantage point. The radiation bath is always 2.7255 K. These 1 in 30,000 defects cause temperature changes of tens to hundreds of microkelvins. One direction of the CMB looks hotter than the other, as big as 3.4 millikelvin, 1 per 800th of a degree Celsius. This dipole has a mysterious origin. The simplest reason is our cosmic voyage. We may deduce that the universe has a rest frame since at this position, we must be moving at this exact pace. This dipole anisotropy equates to a speed of 368.2 kilometers per second, which is close to the proper speed for our location. If we boost ourselves by that speed, or if we keep our present velocity but move 17 million light-years away, we would seem to be at a place indistinguishable from a naive notion of the center of the universe, at rest regarding the observed cosmic expansion. You will always live in this moment after the Big Bang, wherever you are in the universe, even though the light you see has been changed by the movement of the objects and the expansion of the universe. Everything you see seems the same. Depending on your position in the cosmic microwave background, you may notice a dipole matching a certain velocity. Once you consider this, your universe would seem like ours, uniform on enormous scales in all directions. Since the Big Bang's duration and visible distances are restricted, the universe may be centered on us. We may only observe a small percentage of the universe. The universe's size is unknown. We know the universe is expanding because its radiation is becoming longer and denser. Things appear older from afar. The question of where the universe's core is profound, but the answer that there is none is deeper. This was all from my side to guide you about whether the universe has a center or not. Please subscribe to this channel and press the bell icon if you're new to the channel so you don't miss any new stuff.